Very good afternoon, students. Today we will discuss about the other paper, that is DSC, Discipline Scientific Elective, Part A. So Part B is a material science. So I am dealing with this Part A. So the title is Basic Electronics. Okay. So in this basic electronics, so here also same whatever we discussed in the previous semesters, previous classes. Same type of syllabus, 4 blocks. Each block contain different types of units here. Okay. So let me complete this. First one is the semiconductors. Later on, in the semiconductors, what are the semiconductors? You need to know about the what is PN junction diode and what are the VI characteristics of PN junction diode. Next is the transistor configurations and characteristics. What is transistor? What are the different types of transistors are there? PNP as well as the NPN transistor. And in this only, you need to know about that common configurations. Common emitter, common base, common collector. And the other one is the last unit, special semiconductor devices. Okay. So these are the cases we need to know about that in semiconductors as well as the PN junction diode. Okay. Let us go for the semiconductors. Please wait a minute. So I just want to share the screen. Yeah, this is the slide. I'm sharing the PPT. So semiconductor physics. So in this semiconductor physics, today's class is that first of all, you should have a little background of this. What are the origin of energy bands in crystal and how the classification is made up of the solids based on the energy bands. So origin of the energy bands in solid crystal. For example, if you choose an isolated atom, there are discrete energy levels. What are those? 1s3, 2s, 3s, 4s, like that. So that you can say that the electrons which can be occupied by this particular atom. So you can see for a atom, first shell which may be completed by 2 electrons. Okay. And here for a particular atom, you can able to say that second cell, that is 2s2 2p6. First shell is K shell, and other one is second one is the L, and the third one is the M, and fourth one is the N, like that. K, L, M, N, like that. So what is the maximum number of electrons which can be occupied by in a shell 2n square? Suppose first shell, that is small n equals to 1, that is represented by the shell k. If n2 k, like that. So here, what are the maximum number of electrons which can be occupied by in a shell means, if you substitute there 2n square. So that how it will come, I will show you. So if n equals to 1, n equals to 2, 3, 4, like that. This is k, l, m, n, and so on. Okay. Maximum number of electrons. What is the formula? 2n square. So if you substitute 2 into 1 square, 2. That means k shell which can be occupied by 2. 2 into 2 square. That is 4 to 4. 2 into 4. 8 electrons. In which shell, Andy? L shell. That means maximum is 2 electrons. Here is 8 electrons. Okay. Next is 2 into 3 square. 18. 3 3s are 9. 9 2s are 18. Okay. So here 18. But how do you writing and how you are going to be here these electrons which can be occupied 1s2. Here is subshells is also there. The 2s2. Why? Because of n is 2. 2s2, 2p6. Here n is 3. 3s2, 3p6, 3d10. Add these 10 plus 6 plus 2. Total is 18. 2 plus 6, 8 electrons. Only 2 electrons. Getting my point? So that's why here inner shell K. How many dots are there? Electrons? 2 electrons. Next. Other one is the subshells. Okay. 2s and 2p. How many electrons which can be occupied by 2s? 2s2 means 2 electrons are there. Here and here. Next is 2p6. How many? These are the 3 electrons. These are the 3 electrons. Total is 6. Is it clear? So that like that here the electrons which may be occupied by in a shell. So that's what here which is going to be showing that the individual atom energy which is a discrete energy levels. That means 1s2 is completely filled, 2s2 is also completely filled, 2p6 is also completely filled, like that. Okay. Next. So if all the atoms of solids are assumed to be isolated from one another, then they have completely identical electrons of their energy levels. So here you can see that a crystalline solid which may have 10 power 23 atoms. Okay. This is for isolated. For by choosing a solid material, a crystalline solid material, there should be presented these many of atoms, so that like that here those are to be forming a band here. So these are the individual energy levels. By combining all, those are to be forming a band here. Okay. That means when these isolated atoms which are brought together to form a solid, various interactions which may occur between the neighboring atoms. And during their interaction, the higher energy levels which are affected considerably, and consequently the energy levels of these outer shells are slightly altered. That means those are going to be changing here. without violating Pauli's exclusion principle. What do you mean by Pauli's exclusion principle? No two same electrons which cannot be occupied in the same state or same level. Okay? That means electrons is having opposite spin. That means one is up one clockwise, other one is the anti-clockwise. So that plus off and minus off. Okay? Next. So by this individual atom which is going to be showing like this. If crystalline is having more than one atom, if 24 atoms are there, so that these are to be forming a band here. First level, all these combined, those are forming band. Second energy level. Third, that means 1s is different. Okay. So what do you mean? I mean that here. So you can see 1s is this, 2s is, 2p is this one. Okay. This is for only one atom. Here, how many are there? 10 for 23 atoms are there in a crystal. So that for all 1s level, those are combining and those are to be forming a band. 2s level also, 2p level is also. Okay. So that the single energy levels of atom which may split into a large number of energy levels. This one. Next. So there are many atoms in a solid. So the separation between the split energy levels are very small. So the split energy levels are almost continuous and which are set to form a energy band. So you can see here. So 1s2 is completely filled. 2s2 is also completely filled. 2p6 is filled. 3s2 is filled. For which atom, Andy? Sodium atom. So again, for a sodium atom, sodium means electrons. So atomic number is 11 here. 1s2, 2s2, 2p6, 3s1. Okay. 1s2 completely filled, 2s2 completely, 2p6 is also. But here half filled. Next 3p 0. Okay. So that's why here 3s is only one electron, which is half filled. Getting my point? So 1s2 completely, 2p6 like that. So the configuration is given here. Sodium atom. There are energy bands in a solid which are corresponding to the energy levels in atom. If an electron in a solid which can have only those discrete energies, not in a continuous, discrete, dividing, separation that lie within these energy bands which are known as the allowed energy bands and which are generally separated by some energy gap. That gap you can call it as a forbidden energy gap and or else here not allowed energy bands. So these energy bands which may be occupied by the valence electrons which are known as valence band and the energy bands which can be empty or which is occupied by the conduction electrons is known as conduction band. So see here, what is valence band, what is conduction band, forbidden energy gap. So you can able to observe that valence band. So how this band is forming here? Just now we discussed about the sodium atom. Atomic number 11, 1s2, 2s2, 2p6, 3s1. Okay. So this is the outermost shell. This is the outermost shell. So here these are the innermost. That means these are closer to the nucleus here. So there you can able to observe the how the electrons which are occupied. Okay. So that outermost shell. So only these electrons. Actually, how many electrons which can be occupied in a 3s cell and 2 electrons. Okay. But here for the case of sodium atom, only 1 electron is there. That means half filled. Okay. These are the closer to the nucleus. And between them there is a covalent bond. That means between them means electrons. But only for any current conduction purpose, for any participation, any chemical reaction, which electron is going to participate for that means outermost shell electron is only. Why? Because of this is only single one. This is alone. There is no pair of electrons. Okay. So this electron is only possible to participate in any chemical reaction, current conducting purpose, whatever it may be here. So this outermost shell electrons, you can call it as a valence electron. Okay. For only one single sodium atom. For example, if you choose a substance which is having more than 500 electrons, so that how many valence electrons are there for that particular substance? 500 valence electrons. Getting my point? These are combining and those are to be forming a band. That band is nothing but a valence band. Above the valence band, there is a conduction band. Between the gap of the valence band to the conduction band is forbidden energy gap. Is it clear? Okay. So these are the electrons. What is the nature of the valence band? And valence band is completely filled, always completely filled or partially filled. So that here the electron cannot move freely. The bond between the electrons is covalent bond. And above the valence band, there is another band. That band is a conduction band. There only the electron can move freely. But here the band which is always empty or partially filled. Okay. So between the gap is forbidden energy gap. Is it clear? Here electron cannot move freely. Cannot move freely. Here electron can move freely. Okay. So that here there is a covalent bond between the electrons in valence band. By the thermal agitation means here by increasing the temperature to break down the covalent bond between the electrons in valence band, so that the bond which may be broken here, so that by processing or by absorbing such energy by these valence electrons, so that which may enter from the valence band into the conduction band across the forbidden energy gap. So that whenever a valence electron which may enter from the valence band into the conduction band across the forbidden energy gap, that electron you can call it as a free electron. What do you say? Free electron. Okay. So that is the case. So you need to have such a here minimum basics to understand this. Without having these basics, you cannot able to understand and you cannot able to go through this. Okay. Next one. Classification of crystalline solids. So on the basis of forbidden energy gap, solids are broadly classified into three categories. See here, one is the insulator, other one is the semiconductors, last one is the conductor. Okay. Now we will discuss. Very, very important concept we are discussing here. Okay. So let us discuss about the here insulators. So you can imagine that the gap between the valence band and conduction band, which is very wide. Okay. Here the gap is very wide between the valence band and conduction band. Whenever a thermal agitation is to be takes place here, the valence electrons in valence band, so between them the covalent bond is broken here, so that the electron which may acquiring such energy to jump from the valence band into the conduction band across the forbidden energy gap. But the thing is that here this valence the gap between the valence band and conduction band is very wide. So whatever the energy you are giving, so that the electrons which may be fell down into the gap. Why? Because of the gap is very wide. The electron cannot able to jump from the valence band into the conduction band across this forbidden energy gap. All the electrons which are fell down into this gap here. Okay. So that there is no conduction is to be takes place. If no free electron which is available in the conduction band, if the electron is not going to move freely, it does not constitute any current at all. So that the material is not going to be constituted by the current here. Getting my point? So the best example for the insulating materials is wood and insulating tape, rubber, like that. So this may be called here the resistance is very, very high. R value. Okay. So to increase at normal temperature, at room temperature, the resistance is high. By increasing the temperature is also resistance is going to be high here. Is it clear? Next. Second one is the conductors. See here. Valence band, conduction band, forbidden energy gap. All are overlapping here. Okay. So that whenever you are going to be switch it on here, the electron, valence electron, which may move from the valence band into the conduction band across the forbidden energy gap. Why? Because of these are all overlapped here. So that the electron which may move freely here. Okay. So that at room temperature, the resistance which may be reduces here. Whenever the temperature is going to be rises here, the resistance is going to be increased. Temperature rises means whenever such a fluctuations is to be takes place, a more voltage comes out. Okay, a maximum voltage is going to be coming out here. So what is the case here? So the case which is showing here, if you consider a material, a conducting material, which may allow only 500 electrons to that. But whenever a more number of electrons which are passing through that, why? Because of more energy. Okay, maximum voltage is coming out. So that more number of electrons which are coming through that by breaking the covalent bonds between them in valence band. So that material which cannot be hold up of these many electrons. Why? Because of the capacity is only 500 electrons. But if it comes 1000 electrons through that conducting material, by increasing the temperature, So there, here, the electrons between the electron, there is a collision is going to be takes place, colliding with each other and also colliding with the walls of the material. Then the friction is going to be developed. That means temperature rises. Getting my point? Whenever temperature rises here, so due to the friction, due to the more number of electrons, due to the higher potentials, so that the material cannot be hold up of these many of electrons which are passing through that. So that all the electrons which are trying to escape from this material, then the leakage is to be takes place. That's why short circuit is going to be takes place. Okay? At room temperature only, this maybe works good. But when the case of higher temperatures, this cannot holds these many of electrons. This cannot constitute the current here. That is the case. So here resistance is going to be increases. So that what are the examples here? Aluminum, copper, like that. How to overcome this problem? Scientists have been found that other materials, if the gap between the valence band and the conduction band is small, okay, gap is very small, so that which is not overlapped, which is not very wide here, but only the thing is that here the gap between the valence band and conduction band is small here, so that the electrons can jump from the valence band into the conduction band across the forbidden energy gap. So the example for this is silicon and germanium. Silicon and germanium. Valence electrons. What do you mean by valence? Which the atom has a outermost shell. If how many number of electrons are there, those electrons you can call it as a valence electrons. For silicon and germanium, 4 valence electrons. But here at room temperature, these may be work as a conductor, but a higher temperature, these materials can be worked as a good conductors. Good conductors. Okay. So which one? Semiconductors. These may be worked as a good conductors. Please remember this. What do you mean by normal and good? That means a more number of free electrons which are available for conduction purpose. Getting my point? So that here current conduction may be very, very good here for the case of semiconductors. By increasing the temperature, these materials may be worked as a good conductors. At normal temperature, these materials may be worked as a conductors. That is the difference you need to follow. You need to understand this. Okay, now? So this is a very, very interesting topic here. So that is the case. Next, in individually insulators behave like a solid behave like insulator, which may fall out if the solids have even number of valence electrons per atom. The valence band and conduction band are separated by a large gap. And due to the large band, the electrons cannot jump from the valence band into the conduction band. In insulators, the valence electrons are bound tightly to their parent atom. In case of glass, The valence band is completely filled at 0 Kelvin and energy gap between the valence band and conduction band is 10 electron volts. By giving this much of the energy, then only the electrons which may enter from the valence band into the conduction band across the forbidden energy gap for the case of glass material. If you use so that an external electric field cannot provide this amount of energy to the electrons in solid. Next, conductors. So there is no forbidden energy gap. It is observed that valence band overlaps with the conduction band in metals. There are sufficient number of free electrons which are available for electrical conduction. Therefore, the conduction band, valence band, which may overlap here in the case of metals, the electrons from valence band, which may freely enter into the conduction band. So, due to the absence of forbidden energy gap between conduction band and valence band, there is no chance of presence of holes. So, the total energy in conductors is simply due to the flow of electrons. So valence band itself behaves as conduction band due to this reason. Next, last one in the semiconductors. The energy band gap between the filled valence band and the empty conduction band is small as compared to that of the insulators as well as the conductors. The energy band gap is in order to offer 1 electron volt. Germanium, silicon, which are the example for the semiconductors. The for a germanium is 0.7 electron volts, silicon is 1 electron volts. That means if you use a germanium, if you use a silicon, so so due to the small energy band gap in between the valence band and the conduction band, the electrons of Vb can be thermally excited. The electrons of valence band can be thermally excited to the valence band where they are able to conduct small current on application of electric field. So at 0 temperature, semiconductors behave like insulators, but at room temperature, semiconductors behave like a good conductor. So next is the chemical bonds in semiconductors. Semiconductors like germanium, Germanium and silicon have crystalline structures. Both these materials are tetravalent. Electron has a 4 valence electron in the outermost shell. Electronic configuration. So you can see here 4 valence electrons. Can go through this. Four of the germanium valence electrons. 4 valence electrons. 4 out of 4. So 4s to 4p. Like that. And the electron which is escape from the covalent bond and empty space, which is left behind, which is known as here hole. HOLE. The charge of the hole is positive. Next, intrinsic and extrinsic semiconductor. Intrinsic, pure, which is called as a pure semiconductor. Say semiconductor in which electrons and holes are solely created by thermal agitation, which is called pure or intrinsic semiconductor. You need to draw the diagram better to practice. The electrons reaching the conduction band due to thermal agitation leave equal number of vacancies or holes. In intrinsic semiconductor, the number of free electrons which are always equal to the number of holes. Next is the extrinsic semiconductor. So the electrical conductivity of pure germanium or silicon can be increased by adding impurities in the process of crystallization. So why you are adding means in a pure semiconductor there is a equal number of electrons and holes. But actually for any current conduction purpose, it needed a more number of electrons, a more number of free electrons. How it is possible means by adding impurities to the pure type of semiconducting material. Okay. Adding impurities to the pure semiconductor is nothing but a doping. Okay. Doping is based on the doping. Two types of materials are there. One is the P type, another one is the N type material. Okay. But the thing is that if you add impurities to the pure type of semiconducting material, then that type of semiconductors you can call it as a extrinsic or impure semiconductors. Okay. So here two types of impurities are there. One is the trivalent, another one is the pentavalent. So for example, pentavalent elements are phosphorus, arsenic, antimony, whereas the trivalent is boron, aluminum, gallium, like that. So depending upon the impurities, two types of semiconductors which are to be forming here. One is the N-type semiconductor, another one is the P-type semiconductor. Let us discuss about the N-type semiconductor. When you add a pentavalent impurity to the N-type semiconductor, pure type of semiconductor material, you will get N-type. So that by pure form of the semiconductor is either silicon or germanium. How many electrons are there in valence? 4 valence electrons are there. You are adding a pentavalent. Penta means 5 electrons. So that fifth group element which is going to be adding to this pure type of semiconducting material You can able to see the figure here, N-type semiconductor material, fifth group. Okay, 5 electrons are there, arsenic, whereas silicon or germanium is having 4 electrons. 4 out of 4, those are going to be making a covalent bond between them, but only one excess of electron is there. You can see here. But there is no electron, other electron, extra electron, excess of electrons are there to form a covalent bond. Which one is the excess one? This one is the excess one. Okay. So that this atom, which is going to be searching that if any atom is having a deficiency of electrons, so that which can be donate to form a covalent bond. So that here this type of atoms, what do you say, semiconductors, you can call it as a donors. Why? Because of there is excess electrons are there. So that the majority charge carriers in N-type semiconductors is electrons, whereas the minority is holes here. Why? Because if the electron, if it is going to be losing, the hole is going to be created. Electron charge is negative, hole is a positive. That's why here majority electrons are electrons, minority is positive holes. Okay, like that. These are called donors. Next is the p-type semiconductor material. P-type means if you add a trivalent impurity to the pure type of semiconductor. Pure is silicon or germanium. What is the trivalent impurity? Either boron or aluminum. Okay. So you can see the figure here. Boron is a trivalent, means only 3 electrons are there. Okay. Silicon is 4. So 3 out of 3, those are to be forming a covalent bond. But there is a deficiency of electron. Okay. So less amount of electrons are there to form a covalent bond. Deficiency. So that this atom is going to be searching out that if any atom is having excess of electrons, so that it is going to be accept. That atom is going to be donor, and this atom is going to be accept. That means these are called as acceptors. Okay. So that here what are the majority charge carriers? Majority charge carriers are positive holes in p-type. Minority is electrons. Okay, negative electrons. 1 minute. Okay. So there is a deficiency of 1 electron, which is called hole. The remaining 4th atom, germanium, also try to form a covalent bond, and it steals an electron from the neighboring germanium atom. Due to this stealing action, a hole is created to the adjacent, and this process continues. Hole move about a random way due to the thermal effects. And impurity atoms that contribute to holes in this manner are termed as acceptors because they accept electron from germanium atom. Okay. Since current carries are positively charged particles, and this type of semiconductor, which is called as a p-type semiconductor. Okay. Next, Fermi energy level. The maximum energy levels which can be occupied by a particle at 0 Kelvin temperature is known as Fermi energy. Balancing. Okay. So first is which is a intrinsic pure type of semiconductor. There the Fermi level is at the middle. That means valence band, conduction band, middle, which is going to be balancing here. How many number of electrons are there? Those many number of holes are there. Whereas in N-type semiconductors, see here Fermi and gap is more. Fermi level which is moving toward the conduction band. Okay. So N-type, there is a more number of electrons are there and less number of holes are there. Whereas in the case of p-type, a less number of electrons, a more number of electrons. That's why Fermi level here in the case of a pure type of semiconductor, which is balancing here. Whereas in the case of what do you say, n-type semiconductor, which is moving towards the conduction band, and for a p-type semiconductor, which is moving toward the valence band. Okay, so this ends our semiconductors. That means this is the basic one. So this is the basic one here. So we have been discussed. That means in this portion, according to our syllabus, you can see here, see that semiconductors, in this semiconductors only, we have been discussed what is p-type, what is n-type. This is the energy band structure for different atoms here. Okay, silicon and carbon is there, silicon is there, germanium is there. Getting my point? Okay. Tin, SN, tin 50, atomic number. So these are the electronic configuration. Based on this electronic configuration, what are the materials, insulators, semiconductors, conductors? Okay, these are the energy gap, energy bands. Okay, so you need not to be worried. Why? Because of here we already discussed it here. Okay, so energy levels of an isolated atom, how the bands are going to be forming in a crystal, energy band structure here, gap you can able to see here. So which one is a conductor, which one is a insulator, which one is a semiconductor? By observing these, tell me that which one is this one. Okay, this one is a overlapping conductors. Gap is very wide, insulator. Gap is small, semiconductors. Is it clear? Like that you have to estimate. And also we have been discussed that what is a pure type of semiconducting material. How it is going to be forming here. A silicon, a germanium is to be considered. Here, schematic representation of intrinsic pure type of semiconducting material. So which one is a covalent and which one is valence band, like that. Okay. Next is the what do you say, intrinsic and extrinsic we have been. Intrinsic. Extrinsic is there. Based on the doping. Two types. P type, how the hole is going to be created here. Okay. Indium is to be added here. And N type. Okay. So tin needs to be added here. Like that. So these are the diffusion of charge carriers, like that. So other important is a PN junction diode. So this PN junction diode, we will discuss it on coming class. But if you have such a PN as well as GNR, I will tell you in one class. BJT is also there. Okay. So you need not to worry, but go through the slides here, which I have been discussed. Okay. So you can easily understand from this. So if you have any doubts, please ask me. And I will also show you దాని మీద ఏం పెట్టినావు ఇక్కడ రావట్లేదు కీబోర్డ్ మీద తీసేయి chemical bonds and structure, intrinsic, extrinsic, and how the N type, how the P type is to be formed. And also same, some of the multiple questions also there. P type, N type, extrinsic. Yeah, the electrical conductivity of a semiconductor, which is absolutely zero. Absolutely zero temperature is electrical conductivity. Is it finite or large or zero? A room temperature of conduction band electrons are that is valence band dash that of valence band holes in an intrinsic, which is equal to electronic configuration of germanium. Okay, so by atomic number, based on that atomic number, you need to write it down there. Germanium is 32. Based on that, you need to write. Most widely using conducting material, copper and aluminum. In a band structure of solid, width that allowed energy bands decreases with increase in the binding energy of the electron. Band gap of conduction band and valence band of conductor. What is that? About 2 or about 11 or 5 or 0? 0. Order of the band gap in insulator. 10 electron volts. Insulator is more. Okay. Band gap between conduction band and valence band is about to 0. Other is also there. Semiconductors have energy band gap of order of semiconductors. 1, 0 or 10. 1 electron volts. Okay. So this ends our first one. By coming class, we will discuss about the PN junction diode. Okay. PN junction diode as well as the Zener diode. So Zener diode is the best example for the PN junction diode. But you need to know that what are the VI characteristics for the PN as well as Zener diode. Okay. Right. All the best.